Yeah, awesome. All right. Today my talk is going to talk a little bit about history, or a lot of history, some math, and a couple of code examples. And the title of the talk is about how human rights relates to a part of Node core. So here's a passage from the UN Declaration of Human Rights that talks about privacy and security. And there's a lot of versions of this type of language across the world in different rights declarations. But I like the UN version because it uses the word attack, which is really strong language for a document like this. And while I'm going to be talking a lot about people starting businesses and patent fights between academics, the people doing the fighting are fighting to keep your communication secure. Like, that's their actual goal. So the hero of the story today is like the average person. It's citizens, it's you folk, it's all of us in this room. And the villains are the intelligence agencies and the military generals, folks like that. So I'm going to try and follow a timeline, but early crypto, the earliest stuff that you can find is about 5,000 years old, but until about 1949, it's all garbage. And it's hard to talk about specifics because it's also like, most of it was about keeping the design secret, so nobody wrote down much of anything. And it all relied on weak protocols, and it didn't matter how good your scrambling was, your implementation was going to be poor. And a lot of the times, the systems depended on keeping a codebook secret, which is super difficult if someone's willing to shoot you for it. And once these systems were broken, not only were like all the previous messages broken, but a soldier could impersonate your soldiers in the field with your codebook, and that's a huge problem. So some of the first really big computers were built to crack these problems in early crypto. And like an example of that is the known plaintext attack. So one side would plant mines and start listening, and then the other side would come and clear the mines, and they would send a message. They'd be like, "It's all clear, y'all." And when you hear that, you knew that it was an all clear, y'all message, and you can go back and use your big computers to reverse engineer your codes for that day. So designing ciphers was super hard until 1949. The language necessary to describe modern crypto systems was invented in 1949, Claude Shannon. They formalized the tools necessary to describe information transfer, things like compression. And at about the same time, in 1951, the NSA is founded. So during this period between 51 and about 1970, they're feeling really good because they're in control. All funding for cryptography comes through them. They can declare patent applications to be classified in the name of national security. And anyone who wants to go work in crypto goes and works for them. But they're building tools for spies in the military, and you have to agree with what those organizations are about in order to work on this type of stuff. But during the early 70s, commerce demanded a way to perform secure wire transfers. So in 1975, we get DES. And DES is the first serious attempt at a widespread standard for data security. It was successfully implemented in a chip, which made it really super easy to sell. An example is HBO used DES to scramble their communications over the satellite. And the only real weakness in it was that it relied on a 56-bit key. The designers wanted a 128-bit key length, but the hardware concerns got it down to 64, and then government interference pushed it down to 56. So this is an illustration of what that reduction really means. So like every 1-bit reduction reduces the strength in half. So you can imagine what the reduction was from 128 to 56. DES is a type of symmetric cryptography. And symmetric crypto is the easier to understand type of encryption. So you have a key and a scrambling algorithm, and you use that to scramble the data, and your recipient takes the key, and usually the same process, and unscrambles the data using the same key. And if you can keep the key secret, it works super well. DES is still around. You can find it in Node, along with a bunch of other symmetric ciphers by calling get ciphers. This functionality is available in Node because we compile or link OpenSSL when we compile Node. All the crypto in Node is powered by OpenSSL. So if there's a bug in OpenSSL or a security problem, that bubbles up into Node. All right, so big mainframes needed a way to secure their communications, and they also needed a way to store information at rest. IBM researchers, with assistance of the NSA, created DES, which is a block cipher. And that takes a fixed block of bytes and performs a fixed round of permutations on it. And specifically, the permutations are a bunch of substitutions and shuffles. And this is probably the hardest part to understand about modern symmetric crypto, is this S box, the substitution box. So each round, you take a chunk of bytes, let's say 45, and you just do a lookup with that information. So you go to 4, 5, and there you find 68. and then your next round, the value is going to be 68. And you do that 12 or 16 times, and if you shuffle after every time you do a substitution, then you have a really strong block cipher. So DES was a hit, and we still use a version of it today. And even though the NSA reduced the key size, it was secure and widespread, and it got crypto out of the realm of like military and spies and into actual commerce. And this got a ton of people thinking about, what can we do with codes, and how can we apply this information to make money? But it wasn't all commerce and banking. A bunch of these types of folks got involved, a bunch of like activists. Some of the most early crypto newsletters were activist newsletters. And in 1976, two activists, Whit Diffie and Martin Hellman, published the seminal paper on public key cryptography. They and a bunch of smart folks focused on the obvious limitations in symmetric crypto, which is that no matter how good your key, or how strong your key is, or how good your cipher is, your key has to exist in more than one place, and it can be leaked. So their solution was to break the key up into two parts, where one could be leaked and even publicized, and the other one would be kept secret. And all you would need to encrypt a message is someone's public information. And the secret sauce in this lies in a function in math called one-way functions. These aren't two-way functions, that's something else entirely. These are examples of not one-way functions. So given the components of one equation, you can derive all the other fields, or derive all the other fields given the inverse operations. This is like easy stuff. But it gets super hard when the equation looks like this. That x really complicates matters. There's just no one-step solution to this, and that's what they leveraged. So this is the Diffie-Hellman public key algorithm. It's the first really successful implementation of a public key encryption primitive. And here, I'll go through it. Really quick, it's not very complicated. G and P are just numbers, and they're agreed upon by both parties. And you just pick an x value that's less than P. And if you keep that secret, then you've done your job. And you can publicize the result of this equation, the public number. And what's mod? Mod's, it's a math operator that deals with the division remainder. So 5 mod 2 is 1, and 6 mod 2 is 0. Anyway, it's not super important. It just needed one slide. All right, so that was the key generation. This is the key exchange, and this is where the magic really happens. So two people pick their exponents, x and y, and publish their pub1 and pub2 values. And the first person takes the other person's public value and their private value and arrives at C. And then the second person takes their respective bits, and they also arrive at that same C. And the important part is that this C is unique to these two people, and other people can't just derive C given the public numbers. They would have to guess either x or y. And if those numbers are big enough, it's just infeasible. And we're talking about really big numbers. They don't fit on the slide. I tried to have a slide, and it was just, yeah. All right, so that's everything I just described as code in Node.js. You can get your G and your P and your X values. And you can compute the shared secret just by calling compute secret and passing someone else's public key. And that shared secret's important because Diffie-Hellman doesn't describe encryption so much as it just allows two parties to arrive at a shared number given each other's public information, right? It solves the problem of having to transmit and store a symmetric key. Your shared secret is the key. It's the key to your symmetric cipher. So all modern crypto systems are combinations of asymmetric crypto and symmetric crypto. You're going to use asymmetric crypto to negotiate your keys, and then you're actually going to encrypt your data using a symmetric encryption algorithm. All right, so after Diffie-Hellman's published, RSA algorithm is published, and that's one that we should all be really familiar with. RSA takes Diffie-Hellman's a few steps further. Instead of just key generation, the exchange, it actually defines encryption and decryption. This slide also honorably mentions DSA, which is a signature-only algorithm invented by the NSA in 1991. All right. In 1982, RSA, the first encryption company, is founded. They negotiated the use of the patent from MIT, and they set to work. That patent expired in 2000, and that's why we can use it in Node. So they felt they had a problem. Customers really couldn't understand the product. Symmetric encryption is super easy. You have a key, and it locks and unlocks a door, and you can give someone the key and take it away from them. You can change the lock. But asymmetric encryption is it's college-level math. And there are multiple keys and multiple steps to using them. And your key becomes a different key when it's used in someone else's lock. So they wanted to simplify things and put it in a chip and ship it in a box. And they tried, and it didn't work. It would have been the most complicated chip of its day by 10 times. And they designed it, and they built it, and they burned through all this money, and it came off the line, and it just didn't work at all. So they pivoted to a software company, where you would expect, there's Intel inside on the box, there would be RSA inside on your email program that you went and purchased from the store and brought home. And your email would be protected, and it would be like a brand. All right, so this is the RSA algorithm. It's like Diffie-Hellman that it leverages that exponent functionality of the one-way function, but it goes a step further in that it's giving you encryption and decryption. So I don't define the key generation for RSA. It's a little bit complicated so much, but I'll tell you how you use RSA. You would just generate, instead of having a shared secret, you just generate a random string of data, and that's your symmetric key. And then you encrypt that string of data with the other person's public key, and then they'll use their private key to decrypt it, and then decrypt the data packet. So they're recovering their key using asymmetric crypto. And if it's laid out like this, you can see why one's called asymmetric. So email is commonly protected by asymmetric crypto. You would take someone else's public key and encrypt a message that only they could decrypt. And the recipient takes their private key and recovers the message. And an interesting thing is when you do that, if you want to make the message still readable by you, say in your sent folder, you have to encrypt 2 copies, one for them and one for you. So another feature of RSA, probably the most common one, is the sign and verification routines, which is actually just the inverse of what I just described. So instead of you encrypting a message for me using my public key, I encrypt a message for you using my private key. And then you verify I sent that message using my private key. The way this works is that only someone with my private key could make a signature that is verified using my public key. Sorry, that's the most confusing slide. And here's what I just talked about as code in Node.js. You load the keys from disk, and you have a message string, and then you call sign and verify. You can't read that, it's fine. You can't actually generate RSA keys in Node core. I'm not entirely sure why. You have to use an add-on. If anyone in this room can fix that, please do, because it was super confusing at first. All right, so back to the story. In 1989, RSA is licensed to be used in LOTUS nodes. They want to use a combination of RSA and DES, but the NSA wouldn't let them export DES, so they came up with RC2. This is a slide from earlier where I showed you how to pull up what symmetric ciphers you have. You can't see it, but there's a 40 and a 64 after the RC2 and RC4. That's the fingerprints of the politics of the early 90s baked into Node.js. We can't get away from it. You see the 256 on AES? Well, there is one. Those numbers are comparable, 40 all the way to 256, right? And if we lose the fight for strong cryptography, you will see the numbers literally get smaller on this page. So we're kind of blasting through the timeline because you would not believe how long it took for them to write and release this software. But PGP version 1 was released using a combination of RSA and a symmetric cipher that the developer of PGP created. You shouldn't do this. He called it basematic. Nobody took it seriously, and it wasn't until version 2 that we really saw widespread adoption of PGP. And that used a bunch of really strong RSA keys and a new cipher called IDEA, which was invented in Germany. And the patent for that expired in 2012, and that's on the list in the symmetric ciphers in Node. So in '93, the RSA company reports the PGP people to the Exports and Customs Office for violating the patents for RSA. They're just using RSA. It was actually a surprise to them that you had to purchase it. So they neutralized the problem by selling PGP to a company that has a license for RSA. But just a month later, the San Jose Customs Office opens up a formal criminal investigation against the developers of PGP for exporting ammunition without a license. And then 4 years later, in 1997, they just drop the case. And so for 4 years, it's all just these threats and intimidation. And a lot of mystery, too. I couldn't find any real hard details about what was and wasn't illegal at the time because all of the law was being practiced through secret memos and just through opaque government organizations. And they waffled back and forth just so constantly, and nobody could really understand what was going on. But imagine being under investigation for 4 straight years for exporting munitions. So rewind a bit. Go back to 1993. The whole time that they're investigating the email people for exporting munitions, they're proposing a solution, and it's called key escrow. And so how this works would be, there would be a device in your phone, and then before you can make a phone call, it would contact a third party and give them the keys to the encrypted call. So it was a problem. It didn't work. And as we gave them resistance, they kept saying, trust us. And they even proposed the idea, like, they're always like, if you knew what we knew, if you could only see what the type of information that we're able to decrypt using these 40-bit keys, you would agree with us. So it got so fevered that they even let some citizens in to see this information, and they came out and were like, who cares? It's all a bunch of nothing. It's all bunk and not compelling. You would think that they would come out and have been given at least one thing. So nobody wanted to be involved with the Clipper chip. They needed academics to sign on to it, and it just kind of fizzled because the implementation, again, was super poor. The real nail in the coffin was that it was just cracked on the very first day. That was the news article. So the first crack meant that you just had to wait for 40 minutes before the brute force, or the connection was brute forced. And since all this was taking place in the court of public opinion in the media, once the news cycle just became that Clipper doesn't work, the government gives up and moves on to something else. Because this is all just people, they get busy with other things. So while they're not looking, there's this whole period of liberalization with encryption. In '96, there's an executive order, really important. It's impossible to read, but the summary is that the people who are in charge of exporting crypto are not the munitions people anymore, it's the Commerce Department. And they're much faster in streamlining approvals. And then in '97, banks are allowed to use any size crypto that they want. And then in 1998, Al Gore is running for president. He just issues a memo saying that you can use whatever you want, and we should streamline the process for approval, and that's the law we live under today, the Al Gore memo law. All right, let's take a break. I'm glad that this is, anyway. All right, so crypto is more than just math, right? And it's more than just key generation. It's an implementation of a set of protocols like we saw earlier in the last great talk. It defines key generation, key distribution, rings of trust and verification, handshake protocols over untrusted pipes. And every step brings with it benefits and drawbacks. And you can't just say, oh, I'll use RSA and AES and call it a day, because every party has to agree on every detail or things don't work at all. There's no partial decryption. There's no half credit. And your encryption protocol also has to work in the real world on networks that time out. So every step needs a bunch of special attention paid, and it's not like that your app just won't pull up. It's that people's most important messages won't be available to them when it's most necessary. Okay, so since it's a set of protocols, the primitives themselves are actually really secure. You can rely on AES to be secure. RSA, for what it's worth, is secure. So the attacks today don't really focus on the ciphers, they just focus on the implementation. The FBI didn't ask Apple for some master key. They don't have one. So the FBI asked Apple to build a version of iOS that just breaks their implementation. And the people that actually broke the encryption didn't crack the key so much as just remove the negative consequences for guessing too many times. And if it had been an updated model, the implementation would have resisted that attack, right? So other places around the world are pushing for really strict logging that neutralizes security altogether. So what is it if you have a secret key and a password if it's all logged? And you have to retain it for 6 months. The Snoopers Charter in the UK says just that. Every session, every key needs to be logged for 6 months. And really what this is it's just the intelligence agencies are tired of spending the money on saving all this stuff, so they're pushing it off onto the ISPs, and then they'll push it off onto the customers. The version of the law in Russia, the one in the UK is just a threat, but the one in Russia is actually real and happening, and the retention says it's a year, and they're like kicking down doors and seizing VPN hardware. It's what they talk about happening. It's actually happening. So this is what we're up against, right? Even just innocuous commerce is being picked up. They're looking at every packet, right? Especially every plain text packet. They'll build arrays of antennas in backwater nowheres just to pick up your plain text packets better. Oh, that's a limerick. All right. And they're intercepting your data at every opportunity on the wires as it goes through the satellites. And you may trust the intentions of the people at the highest levels of government. I do. but like there are generals that run programs that live from previous administrations, and they're in gray areas, and this is all about secrecy, so it's like these programs exist in secret. The president was surprised by a lot of the things that Edward Snowden put forth, even though they give him all the information he needs, right? So they can attack your implementations in real time. This is a slide from the Snowden leaks. I hope there's no State Department officials or FBI people in here. It would be a problem. And I was going to do some live cracking on this talk, but how many people already spend most of their lives watching something go from 0% to 100% completion? I couldn't make it not a waste of time. So I'll just talk about what it means to crack a couple different algorithms. This is the machine the EFF built to crack DES in the 90s. And this is how you attack symmetric cryptography with custom hardware. The hardware searches for the key space and pipes the output into a detector software. And let's say you're looking for ASCII. Every time the message results in only ASCII, it goes into the detector. And the detector will be like, does it say begin RSA private key or something? And that's how you crack symmetric crypto. There's no verification. You just try a key, and you look at the output. And if it looks like English or language that people speak, then you're on the right track. So there's some code in this repo for cracking DES keys. My desktop could do about 30,000 keys a second. The EFF device did 90 billion. That's why you use custom hardware. 90 billion a second, right? So cracking Diffie-Hellman, super straightforward. All you have to do is guess X. You're given G and P in their public information. That's their public key. They publish it. It's on the internet. So all you have to do is just run X to the equation, and if you got the public number at the end, you guessed it correctly, right? And most everyone uses the same G and P values because they're published as a standard. And this means you can actually pre-compute all the values for X ahead of time, and that's what the NSA has done. It's a program called Logjam. So when you see a public number in the wild like 58, you'd be like, oh, I saw 58. X was 13, right? And this is what our largest supercomputers work on. They do weather calculations, and then they crack your really mundane internet traffic, and then drop it on the floor if it doesn't match some kind of metadata. All right, there's a lot more info about attacking Diffie-Hellman on this website. This is a fantastic website. All right, so cracking RSA is about cracking the key generation routine. And I didn't describe the key generation because it's like 10 steps and it's really tough. But it all starts with two big prime numbers, P and Q. And you get your public key by multiplying them together. And the strength comes from the fact that there are only one P and Q for every N. These P and Q values are also fed into a function that outputs the private key. So if you can factor N and recover P and Q, then you can compute the value for D and start decrypting packets. But the awful thing is that they don't even need to do this because you transfer it around in plain text until it hits Nginx, right? Everything in your trusted environment is in plain text. You need highly available services, and you don't have to want to worry about running it through RSA or caring about keys or updating keys. So how you can help is by encrypting everything, everything. Go overboard. Go into your stand-ups and be the annoying crypto person who asks, what are we encrypting? And then when you get your answer, tell your customers. Because they don't care because they don't know. And if you keep telling them about it, they'll care. I promise you, they will. You have to educate them, right? Publicize the fact that your encryption communications or your communications are encrypted. If you're an indie dev and you don't have customers per se, build encryption into your libraries. Make it easy for people to do it and give them examples of how you would load a key and where you would do it. Or you can make it mandatory. Right? Imagine if you threw an error if something wasn't encrypted. Imagine if Node dropped support for unencrypted HTTP. Wouldn't that be nice? Right? So I'm not sure what tomorrow holds, really. I'm always surprised every day. Security is a really fun topic because your mind's always being blown by what people can come up with. Everything is pretty strong these days. In terms of the tide of power between the people trying to look at your stuff and you being able to keep your stuff secret, we're winning. But quantum computers are coming, and they will eventually crack meaningful RSA keys. And the bad guys are collecting all the traffic and storing it. And waiting for that skeleton key to show up, and it may show up 10 years from now, but if you're still pissed off about the thing from 10 years ago, you want to read those messages, right? And this stuff goes back 60 years. So all you can do is not be an easy target. And because most real-world attacks are not sophisticated. Someone takes an unpatched server, pops root on it, and grabs your keys from your .env files, and then they're in, and then that's all that matters, right? But at the lowest level, it's like someone's crappy job to hack you. And if you make it hard for them, they will just move on. I promise. I've seen it happen. If literally everyone used Tor and PGP and OTR messaging, our intelligence services would actually invest in human capital, human resources, and we would have better intelligence as a result. All right, that's it for my talk. Thank you.